All right, we'll get started again. First, want to talk about the last quiz we took. And so, did you guys figure it out? You know, percent abundances, are those mole percent or mass percentages? Did you go back and check it? Well, actually, it was open book, wasn't it? And so, let me just show you. A lot of people put down the percent abundances are mass percentages. But where do percent abundances come from? Percent abundances come from the mass spectrometer. And the way the mass spectrometer operates is you shoot in a stream of atoms, and the atoms are segregated based on their mass. And so the lighter ones will hit here, the heavier ones will hit over here, right? And so if we feed in like 100 atoms, then you know, most will strike here. Do you see the biggest stream of atoms is here? You know, most atoms weigh this amount. And then we get it's called a mass spectrum. And the mass spectrum is the relative number of atoms, not the relative number of grams, because, right, that's tricky. If you do things according to grams, let's say, oh, over here, you know, even though each atom weighs about 202 U, do you want to total up the whole number of grams here and then compare it to the total number of grams here and the total number of grams here? No, we don't do that with a mass spectrometer. With a mass spectrometer is we just see how many strikes. And so if you have 100 atoms, maybe 30 of them hit here, 20 of them hit there, something like that. And so we call that an atom or mole percent. And so this is the same thing. When you look at the formula for water, you don't say H11O or H12O88, do you? You don't say H12O88 because that's in terms of mass. In terms of mass, you know, hydrogen weighs a lot less. And so we say we have more oxygen in water. There's more oxygen in water than there is hydrogen. Is that true or false? There's more oxygen in water than hydrogen. True or false? It's true if you look at it in terms of mass. Yeah, there's a heck of a lot more oxygen in terms of mass. It's 88. It's mostly oxygen in terms of mass, right? In terms of atoms, it's wrong. Or moles, it's wrong. You know, it's 67% hydrogen in terms of atoms. Anyway, this is how the mass spectrometer operates. The mass spectrometer operates by atom or mole percent, not by mass percentage. We don't total up. We don't send 1,000 grams here and see how many grams strike here, how many grams strike there, how many grams strike there. We don't do that because then you don't have a sense because the atoms weigh different amounts. And so you could actually have fewer atoms, but it weighs more than the lighter ones, which have more atoms but weigh less. Now, percentages are always tricky because you're expected to know. You know, you're expected to know, is that a mass percent or is that a mole percent? It gets especially tricky when we're talking about gases, too. And so we'll go back to this topic later. But let's talk about the whole thing. So those percentages are actually, let me bring up this quiz here. All right, the next thing is this. this is actually, you know, with 3 atoms, it's actually very tricky because we have a choice of hydrogen, we have a choice of oxygen, and we have a choice of hydrogen here. And so the way I tried to keep it simpler by keeping the hydrogens the same. And so we have H2, O16, H2 here. In terms of probability, the probability is, this is where dimensional analysis, I saw a lot of people multiply the probability here by 2. That's not actually correct. The way we do this is like this. Deuterium, which is what we call hydrogen 2, tritium we call hydrogen 3. This is just for these isotopes. Most isotopes you just call hydrogen 2. Has an abundance of 0.015%. And so, you know, there are different ways we could do this. We could say 0.015 out of 100. Right? And then the oxygen 16 is 99.76%. And so we could say 99.76 out of 100 is oxygen 16. And so what we could say is this is the fractional abundance of this is the fractional abundance of this, times the percent abundance of this, 0.015%. You know? Or any variation of this. We could have done 0.015 out of 100 for this, 0.015 out of 100 times 99.76% if we wanted to. Right? I think that's what most people did. Or we'll just do 0.015 out of 100 for this hydrogen, 0.015 out of 100 for this hydrogen, times 99.76%. And so more people had, well, success. Well, some people figured this one out.
Why do we leave 1%?
I'm sorry, why do we leave 1 as a percentage? Because we want a percentage at the end. This is just dimensional analysis, and so we look at what we want at the end. We want the units to be percent. So how can we get units of percentage? You aren't given the formula. Did I tell you about my engineering experience with dimensional analysis? It was a very interesting experience. I was taking an engineering class at UCLA, and the professor gave a problem. But you know, he didn't give the formula. He never gave the formula in class. The book didn't have the formula for this particular problem, as we went through it. But he gave all the variables and all the units, and he asked for a specific dimension. And so I thought, oh, this is just a dimensional analysis problem. Just string up the units and string up this until we get the desired answer, because I was so used to doing dimensional analysis, being a chemist. But it turned out that, you know, that like 70% of the class couldn't get that problem. They just left it blank, because then I thought, wow, they didn't get it. And I just figured they didn't have that much dimensional analysis. You know, they're so used to being given an equation and then just plugging it in. Right? And so this is a dimensional analysis type problem. For example, here, if we left 2 of them as percentages, let's say 0.015% times 0.015%, you know, then this is going to give you, you know, this is going to give you percent squared. What is the physical meaning of a percent squared? Is there? No. No. Actually, in that engineering class, there were very few chemists. Just to be fair. So I think if there are a lot more chemists in there, it would be different. Also, 2. You know, 2 out of 100 is like 200%, right? And so if you're doing 2 out of, well, not 2 out of 100. This is 2 out of 1. And so that would be like 200%, right? 200 out of 100 is the fractional abundance. So if you're doing 2 times 0.015, then I'm looking, okay, this is a pretty big fractional abundance, 200 out of 100, right? Times, you know, 0.015 out of 100. And so this doesn't make sense. I understand that there are 2 hydrogens, but you just don't double this. Is that, so, This is it. The thing is, you know, like I said, I've given this problem before on tests, but I made it actually a notch harder, so I thought I was being fair. But this is H1O16 H2. This one is more difficult. If I gave something like this, do you know what you have to do? What is the percent natural abundance of this? Well, now I just kicked it up a notch. Do you know why? Okay, you tell me. H1, let's figure it out. H1 is 99.985. And so we'll just go, how about we'll just take the hydrogens. We'll do 99.985 out of 100, or H1, times 0.015 out of 100, or H2, times, well, O16 is 99.76%. This gives it. Is this the answer? The percent natural abundance of a water with one hydrogen 1, one hydrogen 2, and one oxygen 16 is this. True or false? False. These are true. You know, this is going to be the same number. And so what's the difference here? Like I said, I purposely put 2 deuteriums on there. Well, there's another reason I put 2 deuteriums, because if I put 1 and 1, then it's a little bit more tricky. Do you know why? Can somebody tell me why it's a little bit more tricky? The reason it's more tricky is because this is false, because there are 2 ways. 2 ways to make. The 2 ways we can make is the left hydrogen is an H1. And the second way we can make this is if the right hydrogen is H1. And so when we have these random collisions, and this happens, and so there are 2 ways of making this. Since there are 2 ways of making this, you know what we have to do to the probability? Unfortunately, we have to, add them together. So the probability of this one is this, the probability of this one is this, and we add them together. And so we must combine the 2 probabilities.
But for example, what if the question only shows the first way, and we start to assume that there's 2 ways?
This one, there's only, I mean, both of the hydrogens are the same. They're both deuterium, so there's only one way. Both of them have to be deuterium. And so we can't have one deuterium here and something else here. Both of them have to be. And so this one is just one way.
How are they different if they're flipped over?
They aren't different. They're the same molecule. It's just when we're looking at the reaction statistics or whatever, you know, there's one way, you know, if you were to fix this in position, you know, then there are 2 ways of making this. But once you let them free, then you can't tell the difference. They're the exact same molecule, and so that's why when we say something like this, you know, it's just how we can make it. We have to double the probability. I mean, you could have figured this out. The way you could have figured this out is you figure out all the molecules present, and then you see if they add up to 100%. I actually gave this on a test one time, and I asked people to add up the percentages to see, do they combine to add up to 100%? And then I asked them, is that experimental error if they don't, or round-off error, or some significant error? And so when you do this and you add up all the percentages and you only account for one way of making this, the percentage comes way below 100%. But, you know, this would be a challenge problem for sure. on anything. But since it's an open book, a lot of people say, can't we have a take-home test or an open book? You know, my vision of take-home exams is a total nightmare. You know, every take-home exam I've had, it just took too much time. You spend all your time on one class, you ignore all the other classes because the take-home exam's too hard, you know? And so I hated take-home exams. But, you know, still people ask me, take-home exams or... Also, notes, you know, if I allow you to have notes for the test, then I'm going to have to make it harder, you know? I just want to have no notes, no take-home exam. Maybe I'll give you a take-home quiz. All right, so anyway, we get the percentage for this and the percentage for this, and then we just combine these. To make. So the trick, I mean, they look exactly the same. It's just if you have an oxygen there, one hydrogen comes from here, or one hydrogen can come from here. That's fixed. All right, once we figure that out, then we can go on to C here. How many grams of... G2O. I used to use this stuff all the time, but it wasn't this. I used to use this stuff. This oxygen-16 wasn't isotopically pure. And so this was just your average oxygen, which is 16, 17, and 18. We'll call this D2O. D2O. I used to use it all the time because of its nuclear properties, not because of its chemical properties. Its nuclear property, the nucleus of deuterium is not magnetic, whereas the nucleus of hydrogen, 1, is magnetic. And so since it's non-magnetic, it's invisible in nuclear magnetic resonance spectroscopy, or magnetic resonance. Anyway, going to this next question, if we have 250 mils, you know, 250.00 mils, then we need to convert this to grams of H2O by using the density at 24.2 degrees C. The density at 24.2 degrees C, you should have how many sig figs for that? So it's 6 sig figs? 7 sig figs? 6 sig figs? From the table. And so once we get grams of H2O, then we convert that to moles of H2O using the molar mass. And the molar mass of H2O is what? You know, the molar mass, I normally tell you to go 2 decimal places, so it comes out to 18.02 grams per mole. But here we're given 5 sig figs, we have 6 sig figs here. Do we want to artificially keep it lower? And so this would be an exception. This would be a case where you probably should throw it not to 2 decimal places, but you should go to at least 3 or 4 decimal places so that we don't cut the precision of our final answer because of some. And so I would extend this farther, which we can do. Need at least 1 more sig fig. Most chem problems, if you look at chapter 4, we'd never have to do that because in chapter 4 we're never given anything with 5 sig figs as our given, right? And so in chapter 4, the stoichiometry stuff, 2 decimal places is fine. It's just this chapter 2 stuff where we have so much high so much high precision, we can take it out. But let's see what the other ones are before we do this. The other ones, we go from moles of H2O to, no, we go from moles of H2O to, we go from moles of H2O to moles of D2O16. How do we do that? How we do that is we have the percent by mole abundance. Right? Although it's not specified, it's by mole. You should know it's by mole because all those percentages, natural abundance percentages, are atom/mole percentages. And I know I on purpose didn't specify whether it was a mole or mass percent. You know? So I expected you to look it up in the book. All right, so once we have moles of D2O, then we have to go to grams. And so how many grams of D2O are there? O16. So I need to scroll up here. And so when we're looking at this, we know the mass of deuterium to 4 decimal places. We know the mass of O16 to 4 decimal places. So we're going to have 4 decimal places plus 2. We're going to have 6 sig figs in the molar mass of D2O16. And so this is going to give us 6 sig figs when we go from moles of D2O to grams of D2O. And the grams of D2O is just going to be what? 2 times 2.0141. And then O16 is 15.9949. So 6 sig figs,
The step before that, where you get a mole percent. Is that's from part A?
That's part A,
And
right.
Is that a percentage, or can you just, that's mole, and you go to the next step and you do mass?
The mole percent is this. Actually, let's just calculate it. It was what, 0.015 out of 100 times 0.015 out of 100 times 99.76%. And so what does that come out to?
2.245
2.245
times 10 to the negative 6.
times 10 to the negative 6%?
Yeah.
All right. How many sig figs are we allowed here? We're only allowed 2 sig figs here. And so here, you know, what we'll do is we'll subscript it. So this is going to be 0.0050. So we'll just do 5 zeros, a 2 sub 45%. And so this conversion factor here, I would write like this. I'd write 0.50, 2 sub 45 out of 100. That means there are going to be 2245 moles of what out of 100 moles of what? This is moles of D2O16. Oops, I don't need the 2 up there. I need the 2 down here. If I call it deuterium, or, you know, in our standard notation, it'd just be H2 sub 2, O16. Out of 100 moles of what? H2O. And so if I had, I'd have to add, how many decimal places would I have to add? I'll tell you. We just move this. Let's move the decimal place. 1, 2, 3, 4, 5, 6. move it 6 over. Or actually, let's move it 6, 7, 8, 9. We'll move it 9 over. And so I get 2,245 out of, now let's move this 9 over. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So for every 100 million water molecules, or for every 100 million moles of water, I'll have 2,245 D2O molecules, or 2,245 moles of D2O. And so I just, atom and mole percent are the same, or molecule in this case. And so, actually not 100 million, what is that, 100 billion. Out of 100 billion water molecules, 2,245 of those will be D2O. We don't want to do this by grams. Does this make any sense to do it by grams? For every 100 billion grams of water, how many grams of D2O you'd have? It's too complicated. This is why chemical formulas are represented as mole ratios or atom ratios rather than mass ratios, because mass ratios don't tell you anything. You know, you'd have to know how much each atom weighs. Okay? And so we'll just say molecules, or we'll just say moles of molecules. And so basically, moles of water cancels out moles of water, leaving us with moles of D2O. Once we have moles of D2O, then we have the masses of the individual isotopes, so we can figure out how many grams of D2O we have. That gives us the grams of D2O. And part. Right. Then I threw on this last problem. The last one, I wanted to see what you do in this particular problem here when the information's missing. So we need to go from grams of D2O to milliliters of D2O. But what do we need in order to go from grams of D2O to milliliters of D2O? We need the density. And so the reason I wanted to see what you guys did was because I didn't give you the density of D2O. And so what would you do if you're not given the key piece of information to solve the problem? A lot of people will say, hey, you know, I wasn't given that piece of information, so I'll just give up. Right there. But we don't have to give up, because maybe, you know, so far all these answers have been very precise. Actually, let me back up a step, because I forgot what I was going to say about the sig figs. Since we're only allowed 2 sig figs here, then I wouldn't care. I would say, okay, this is fine because we're going to be limited by a given piece of data. You know, our original was 5 sig figs. This, which was given, is only 2 sig figs. Therefore, no big deal if I use 4 sig figs here. Does it make sense? That's what I was going to say about the sig figs there. So, what would you do if you're missing this key piece of data? Well, this is it. I wanted to see if you try to make an assumption. You know, assume something in order to come up with, you know, an answer. You know, the more quantitative, the better. And so one of the things is like this. One of the things is, what do you think? Is a D2O molecule bigger, smaller in volume, in terms of size, than a regular water molecule, like a H1, 2O? Is it bigger? Having an extra neutron in the nucleus makes the atom physically bigger? Twice as big, maybe? You know, because a hydrogen 1 only has a proton. Now you throw in a neutron in there, does it make the atom twice as big? What do you know about isotopes? This is something I mentioned a couple of times. Isotopes are going to have the same chemical properties or different chemical properties. Same chemical properties or different? They have different physical properties. They're heavier. But what about the chemical properties? When you drink that D2O, better watch out because that D2O is going to behave differently than H120. All right, obviously, no one caught this? I talked about it a few times, but no one caught it? They have the same chemical properties. I also talked about the size. I don't know if it's in your notes, but I talked about the size of a deuterium versus the size of a hydrogen. What did we say about the size? Maybe it's in your notes, maybe it's not, but if it's not in your notes, you missed it. The size is about the same, right? The size is dictated by the proton's attraction for an electron. Does a neutron change that? No, I mean, proton's still +1, electron's still -1, right? The size depends on how much that proton pulls in the electron. And so what we're going to assume is we're going to assume that the volume of a D2O is about the same as an H2O. And so then we're going to just estimate the density. You know, deuterium weighs about twice as much as a proton. And so rather than having, what we do though is this. You know, we would have a heavier water molecule per milliliter. We're going to still think the same number of water molecules packs that milliliter because a neutron really doesn't change the overall volume of a hydrogen atom, right? Of course, the nucleus is going to be different. The hydrogen atom isn't. And so all we do here is we make an estimate. Okay, H2 weighs 2.01 grams per mole. We have 2 of those. And so we'll just multiply that. We'll get 4.02. And then we have an O16, not O16. This is just regular, this is O16 we're talking about. And so O16 weighs 15.99. 15.99. Those 4.02 divided by 15.99, 1601. Right. And so a D2O16 weighs about 1601. Oops, that's not right. 20.01. And so we'll take the density of water and then just multiply it by a ratio. We take the density of water and then times this by, okay, it's going to be 20 parts heavier than regular. Regular water is 1801, 1802. And so this is just your average water. We're going to replace all the average waters, which add up to 1802 grams per mole, with D2O16, which weighs 20.01. And so this would be the density. It would increase by a factor of this. Does that make sense? And this is just an estimate, right? Because we're making an assumption that we're going to pack the exact same number of water molecules in a milliliter with D2O16 as we would with regular water. You know, all right, any questions on the quiz? No? And so, yeah, this was a challenging quiz for sure. So, what about today's? I don't know. How far are you guys on with the titration? Maybe we'll skip today's quiz if you guys need maximum time. Do you want to take today's quiz or skip it? Well, it's up to you because it's 5 points. You could either think of it as easy 5 points or potentially lost 5 points, right? And so if you think of it as easy 5 points, you want it. But if you think of it as potentially lost 5 points, then you don't want it, right?
It depends.
I'll give you a preview of the quiz and you tell me. You want a preview of the quiz? I'll show you the quiz. You tell me whether you want to take it or not. How about that? Is that fair? All right, can you read that? Change the font.
You get a phone.
Home?
Oh, okay.
It depends on how much time you need for the titrations. You want to take this or leave it? You tell me. Well, let's say we'll do it by a quick vote here. Do I need to discuss today's lab, or does it seem pretty straightforward? Straightforward, right? Just weigh out the samples in an Erlenmeyer and titrate them. And so let me take a vote. Some people will finish quite early. So take it. All right. Then you're going to have 5 points less quiz, all right? 5 points less quiz. We're not going to have a quiz this week. We have an exam next week, though. All right, so I'm going to stop talking. Uh-huh.
So we lost 5 points or just
No, it won't be included in the grade. So your total grade will be 5. Your overall points will be 5 points less. That's it. It depends on your quiz percentage. You know, if your quiz percentage is higher than your regular percentage, of course you want to take it, because the quizzes add up to an exam.